Welcome back to the lab. Today we're going to continue working on the electronic load project, and I'm so excited. This thing's going to be a beast, and this project's going to be a blast. Well, at least I hope so. I think it will be. It should be a lot of fun. Today we're going to push it forward by looking at some of the critical components in the design. We're going to look at what's available today with regards to linear FETs and some of these digital to analog converters and analog to digital converters, the digital isolator. We're going to find some of these parts and just find something that seems to fit the architecture, fit the project well, and see what they can do for our application. Let's dive in. The first component that I really want to dive into is the Linear Mosfet. And the reason why is because this thing is literally the heart and soul of this electronic load. This is the component that defines the maximum power, the maximum voltage, the maximum current. So really everything else in the design is really there just to support this part. This is the thing that's actually dissipating the power. Yeah, I think every other circuit in this design either drives or protects this part. So it's a pretty important decision. But it's not really different than what you might know as a regular N-channel MOSFET. The difference between a linear FET and a MOSFET is typically MOSFETs are made for switching applications where they're meant to turn on or off as fast as possible. So the region where the resistance of the MOSFET is dynamic, where you can use it as a dynamic impedance like we want to today, that's pretty small. That's a small region. So it becomes hard to control because if 10 millivolts changes the resistance by 1,000 ohms, well, that's kind of a problem. So what they do is they stretch that region out a little bit more. There's a little bit more gate capacitance, but that ends up being a feature, not a flaw for this application. Basically, we're just stretching out the linear region of the part, or that region where changes in gate voltage change the effective resistance, the RDS on, well, RDS, the drain to source resistance. It's not fully enhanced, that's the point. The drain to source resistance of the linear FET. Very exciting stuff. So I was looking at a few different parts, but there were a couple that really stood out to me. And I want to talk about one of those today. This part really stood out to me. And if you're wondering why, well, here it is. So there's a lot of different linear FETs that are available, even from IXYS. IXYS is kind of the industry leader here. But this part specifically has a really high current rating, a really high voltage rating, and a relatively low price. Like, that's really not bad. Like, for the heart of this design, for the thing doing all the heavy lifting, $10, that leaves some room for cost of supporting components without really going crazy. And I mean, 40 amp electronic load is nothing to sneeze at. We're going to dive into that in a moment, though. So with this part in mind, I just want to dig through the datasheet for a moment, and I want to take a look at a few things, specifically the safe operating area of this part and what that means for the current voltage and power rating of this electronic load. See, we could design it so that it's always we could design it very conservatively, such that the maximum current is set to if we were at the maximum voltage. But if we want to be a little sneaky, I think usually you'd want a high current at a low voltage, or a high current at a low voltage, or a low current at a high voltage. Yes, you're not usually out in that maximum power peak, at least not with what I normally do. So let's take a look at the safe operating area. I love linear FETs. Linear FETs are so cool. They're so cool. Look at this thing. So they know that this part is such a beast that they give you two safe. You don't normally get the safe operating curve when the thing's hot. Like, you don't normally get this. You usually have to derate it. Well, yeah, whatever. It's a linear FET. Super, super cool. So the curve on the right, this is the one that we're going to have to use for our fault timers, for our fault current limit and our fault voltage limit. So let's think about that one first. Let's say that we demand that our fault timer resolves the fault in 10 milliseconds. Let's make that a requirement. So that means that we're following this curve right here. Okay? And so if we want to allow a fault to occur at a voltage of, let's say, 1, 2, 3 because this is a logarithmic curve. So let's say we want a fault that's allowable at 300 volts. If we want to make that the voltage rating. But someone drops, like goes from no load, and you have it set to like, 10 amps, something normal. The FET gets fully enhanced, and then they drop 300 volts on the front end of this thing. Talk about a surge current. Okay, never do that. But let's say they did. If we can resolve this fault within 10 milliseconds, that means that our fault current, our peak fault current, would need to be limited to 3 amps. That's not a lot for our 40 amp MOSFET. Okay, let's bring that down a little bit. Let's say we limit the voltage allowed to 100 volts. Okay, well now we're coming up this curve. That looks okay, all right? Coming up this curve, we go all the way up to the 10 millisecond line, and we can get to, what's that, about 9 amps. That doesn't feel right. I don't like that. I don't like that for my fault current. So let's say we make our requirement a little more extreme. Let's say that we say we need to resolve it in 1 millisecond. Well, that means we can get up to around 30 amps. Around 30 amps. So as long as we can resolve our fault in 1 millisecond, we can handle a 30 amp fault. Cool. So that means that we can handle about, that's fine. So we need to make sure there's a little bit of margin because we don't want to be triggering this overcurrent protection while we're really operating. So perhaps what we would do is say, let's add 20% margin. This is just pretty rough stuff at the moment. So that means we want 6 amps of margin. So that means we have 24 amp right in there. And on the voltage side, let's add a little bit of margin as well. Let's say they can go up to 90 volts. So then this would be the region where we would allow our load to operate. So that would be up to 28. What did I say? 26? 24. So it'd be up to 24 amps and 90 volts. Wow. Okay, so just 24 amps, 90 volts. That would actually be up to 2 kilowatts at that maximum power peak. And that would be our nominal output. That's actually pretty cool. So if we drop our voltage 10, 20, 30, 40, 50 volts, and we were to come up that curve, right? So we're coming up, and then we limit ourselves to that same 1 millisecond. Whoo! We could get up to a pretty high current. That's pretty cool. We could get up to 10, 20, 30, 40, 50 amps of fault current. 50 amps of fault current would be pretty darn cool. So that would mean that we could get our peak current if we apply that same, what was that, 20% derating. 10, 20, 30, 40, 50. 50 times 0.2, so we'd want 10 amps. So that means we could have a 40 amp output current. Isn't that pretty close to our limit? And actually, that's not within the safe operating area all the time, because we need to stay underneath that DC safe operating area curve at all times. So if we design this for 10 amps up to 30 volts, and we need to start derating, and we cut off. If this is the profile that we follow, that should be well within the capabilities of this part. So that means we'd be looking at a 10 amp nominal max, a 90 volt max, and our maximum power would be, what's that, 30 times 10? Is that right? Let's check that. So we got a 300 watt corner right there. And what's the other corner? We're up at 90 volts times 3.5, 315, okay, about 300 watts. We're riding about 300 watts max. So that means we can do 300 watts, 10 amps, or 90 volts with a single stage. And that might guide you to where I'm leading on this. So this is just a single MOSFET. This is just a single part. Honestly, getting 300 watts out of a single part, that might be a challenge. That's a lot of power to get in and out of a part. I don't even know if I would want to push the power any higher if I could. Like if I could find a better linear FET, I don't know if I'd want to increase the power density that much. But we can put multiple of these stages in parallel. We can put multiple FETs in parallel. We can do all kinds of things to try to get this output power to where we want it to go. And that's okay. I'm totally okay with that. Because by distributing this power, maybe even if we double it, if we put 2 of these FETs in parallel to get 20 amps, 90 volts, or 300 watts, whichever comes first, with a fault current of 24 amps and a fault voltage of 100 volts. I like it. I like it. This just might work. That's kind of where we're at. I feel like I need to take a note. I'm going to do that. Awesome. I just took that note so that I can remember that later on in the video. But that pretty much covers what I wanted to talk about the linear MOSFET. Let's move on from the linear MOSFET and let's talk a little bit about the ADC. Now that we know our voltage range, we can figure out if that 10-bit ADC is going to be enough. It's still important that we understand how this part operates. And here's fundamentally what we are doing. When we pull up a calculator, we have some amount of voltage. In this case, 100 volts is the maximum that we need. And basically what we're doing is we're taking those 100 volts and we're dividing it by that 10-bit resolution. So that ends up being 2 to the 10th. 100 volts divided by 2 to the 10th. Excellent. And so that means that once we divide that 10 volts, or that 100 volts down to the range of our ADC, so if we scale 100 volts to 3 volts and 0 volts to 0, that means that we would have, every tick of that ADC would be equal to 97 millivolts. That's not bad, because we take the 100 volts, divided it by our resolution, and basically that means that our 10-bit ADC would provide 97 millivolt precision. Precision is basically the distance between the steps, and accuracy is how close that is to the real number. So that would be 1 tick equals 97.6 millivolts. That seems perfectly adequate for our application. Keeping that in mind, assuming that our ADC was perfect, if you take that 97.65 millivolts and we divide that, I got the calculator here, divide that by 100, that is basically 0.1%, 0.097%. So that means that we might be off by 3 or 4 encoder ticks, we might be off by 3 or 4%, or not encoder ticks, 3 or 4 ADC counts, but hey, it's no big deal. That's no big deal, at least not on a first prototype. Increasing the resolution of the SPI ADC won't really be a problem. The plan is to drive this off of a 3.3 or 3 volt reference. Haven't really decided yet, but I'm feeling 3 volts at the moment. And we're going to take a look at what type of power source makes sense. This has a really low power consumption, so we might end up using like a precision type of power supply just for this component. We shall see. However, I think that 10-bit ADC is fine. This one stood out to me just because it's cheap. I think in the small quantities we're working at, it's like $1. You know, it's not too bad. I think that will be perfectly sufficient. Similar type of concept here, but now we're looking at the DAC. Simply because 10-bit DACs were a little more expensive, decided to see what the 8-bit DAC could do for us. And so now it's kind of the same calculation, but we have less steps. So now in this case, I'm still dreaming that we can get this design up to 20 amps. I want to get a 20 amp output, even if it means 2 FETs in parallel. So let's consider 20 amps on the output for a moment. If we've got 20 amps on the output, and we have a 8-bit ADC. That means we're looking at about 78 milliamps per tick. That seems all right. 78 milliamps per tick is certainly sufficient for what we're doing today. Got a little visitor. I'm sure you heard that shake, but she is sure cute. Anyways, here's where we're going with that ADC. Basically, we've got, what was that, 78 milliamp resolution. So 78 milliamps, take that divided by our 20 amp set point. That ends up being 0.3% error, so significantly more error. But I kind of want to live with that because this DAC is real cheap. It's real cheap. And DACs get pretty expensive pretty quickly. I like the 8-bit DAC. I might regret that. So with this in mind, that 0.39, that 0.4% error, that's not what I would call ideal. Perhaps it's not great. But let's think about this in terms of something that we care about, right? The reason why this is important is because any error in this DAC is going to be directly reflected in the output current, because that DAC is defining the set point for the current regulator. So the error amplifier is comparing to this DAC as its absolute voltage and current reference. So 0.39% error is going to come out as, well, yeah, 0.39% error. So that means that our 20 amp set point could be as high as 20.07 amps. 20.07 amps. Can you believe it? Man, your electronic load is 20.07 when you wanted it to be 20.0. Throw it out. No, honestly, like, from my perspective, that's pretty darn close, right? There's going to be temperature effects. There's going to be all kinds of stuff impacting the accuracy of this system. So, I mean, maybe nominally we should design it to be a little more accurate. But for me, if this is on my bench, it's going to be basically at room temperature most of the time. It's going to be kind of like in a lab environment. It's going to be kind of babied. Like, it's not going to be out in the wild, like up on top of a airplane, like freezing and sub-zero temperature. Like, it's going to be in a pretty nominal lab environment. And 20.1 instead of 20, I'm not going to lose any sleep over that. Thankfully, our monitoring circuit is going to have that increased 10-bit resolution. So if we find that the ADC is more accurate than the DAC, we could always have a little bit of feedback in the micro where, you know, it might push that DAC reference around or do like a self-calibration routine. We could do that periodically just to align that range pretty well. But I'm hoping that isn't necessary. I'm believing that this is accurate enough for what we're doing. So we're going to move on because we've got a couple more components to talk through. Two that I specifically want to talk about are this power supply right here. This power supply is from Meanwell. It's very similar to one of the modules we've used in the past from them in the UPS project. However, this one's got a bipolar output, so it's got a plus or minus 15 volt output. You give it 12 volts in, it gives you a bipolar 15 volt supply. Perfect for our op amps. Now, what we're going to need to do for some of our low voltage digital circuitry is have a precision or some precision voltage references that come off of that to drive our DAC. Maybe those are LDOs, maybe those are shunt references that have a pretty beefy output current. But, you know, we're going to need some small amount of milliamps of precision 3 volt power, and we're going to need a general 15 volt input. So we've got a 1 watt and a 2 watt version of this part. Whether we need 33 or 67 milliamps, we will decide down the road once we get through this detailed design. But I'm pretty confident that 2 watts will be plenty for the gate drive and circuitry that we're driving out on the high voltage side. That in mind, that means that our digital isolator is kind of important because this could end up being one of the critical loads. This might be one of the highest current loads. And the one that we found is unsurprisingly from Silicon Labs. And the reason why we picked this part is because it's got 6 channels, and it's got one of them that comes from the high voltage side back to the low voltage side, and 5 of them that come out. So that'll be our SPI signals and 3 chip selects coming from the low voltage side from the micro, and then 1, which is the MISO, the master in slave out, that is coming from the other side. I love these things because they do RF modulation inside of them. Demodulate, basically capacitive isolation barrier rated for 5 kV. These are pretty sweet. They're more than we need, but I would rather over-engineer it for $2, and $2 is cheap insurance. 5 kV isolation barrier. Let's see if we can find the power consumption. That'd be just about the only... That'd be about the only thing that could limit this. Oh, there we go. Supply current. Supply current. Okay. So it looks like we're looking at around megabits per second. Let's assume we're at 40. So we're looking at about 6 milliamps. That'd be times 15 volts. So we're looking at about 0.09 watts. That ought to be all right. That should be fine. That'll be fine. Oh, that's really low power. We might need to think about this a little more. Perhaps we'll need to run our digital isolator at 5 volts. Or we might need to have a buck converter. We might need to have a switching supply to source this part. Mark that one for a... we need to do a power budget. Because, wow. Yeah, that could be a little tight. So, performance-wise, I love this thing. But it might make the power architecture need to shift. We might need to add a second one of these modules to drive the digital circuitry. So we might need the plus minus 15 for all the analog stuff, and maybe we use the 1 watt part. And maybe we need a 2 watt part that's like 5 volts that we can regulate down to 3.3 or 3. But the high level structure is going to be about the same. We're still going to have the isolated module and regulate it down. So those are the critical parts that I really wanted to walk through. The FET was absolutely critical. The ADC resolution, the DAC resolution, the SPI isolator, the power supply, those are all super important parts of this design, and I really wanted to share this part of the process with you. It might not be glamorous, it might not be parts exploding and FETs flying, but it is so important. If we pick a linear MOSFET that won't meet the specs of the design, it won't meet the design intent, that means we're never going to succeed, right? It doesn't matter how well we do the rest of the project if we start with a bad part. It doesn't matter if we design something that's good if it's not safe. It doesn't matter if the compensator's great if it can't drive the gate of the FET, right? So we need to make sure that the whole architecture is built up well, and critical part selection is a big part of that. Well, that's about all I have prepared for you today, but if you like this video and you can't wait for more, don't forget to hit that like button, get subscribed, or let us know how you feel in the comments. I'm really excited, and I hope that you are too. Coming up soon, we're going to be diving into driving that relatively high capacitance gate on the linear FET, as well as the overcurrent protection circuit design. It's going to be awesome. It's going to be awesome. I can't wait. If you'd like to support the channel, don't forget to check out the links in our description. You'll find our Twitter and a link to our Patreon if you want to support us directly. Thank you to those who have decided to take that step. It really helps us out a lot. Thanks. But most of all, I hope that you learned something great today. I hope you enjoyed, and I hope to see you again soon. So thanks for watching EE for everyone, and thank you for staying till the end. Bye.